Hello everyone. In the continuation of our previous session on introduction of recurrence relation, where we learned that what exactly a recurrence relation is and how we can generate it from some sequence. Now in this session, I am going to discuss about the solution of recurrence relation by using the method of undetermined coefficient. Okay, so let me share my screen. So this is the definition that we did in the last session, that an expression in which every terms of a sequence can be expressed in terms of a previous term, one or more, is called as a recurrence relation. Okay, so now let us see that what is the standard form of a recurrence relation and how one can move to find the solution of the recurrence relation. The standard form of a linear recurrence relation, which do have n number of terms, can be written as Cn into An plus Cn minus 1 into An minus 1 plus C0 into A0 equals to f of n. This is what we call as a linear recurrence relation. This is what we called as the linear recurrence relation of uh, nth order. Like the order of this recurrence relation is what? The order of this recurrence relation is n. Now moving ahead, what are these C? This is very much similar to the linear differential equation of constant coefficient. So here we call these Ci as the constant. We call them as a constant. So if all of them are constant, we call it as a constant coefficient linear recurrence relation. If they are variable, we called it as a variable coefficient. Okay, so as per the coefficient, the naming is done. If coefficients are constant, we call it as constant coefficient linear recurrence relation. If coefficients are one or more than one coefficients are variable, we call it as a variable coefficient recurrence relation. This Fn is called as function of n, which is free from an. Which is free from an means it should not have any term of an. It is purely a function of n. It may be in terms of trigonometric, it may be in terms of exponential, or it may be in terms of some other nature, the mix-up kind of nature. When I'm asking to find the solution of this recurrence relation, so that means I'm interested to find the value of an which satisfy this equation. Any value of an which satisfies this equation is called as the solution of this recurrence relation. Remember the solution of linear differential equation? Any value of y which satisfy y means the dependent variable. If the nature is y equals to fx, the value of y which satisfy the equation is called as a solution. And the solution over there is what? Sum of CF and PI. Over here, the solution of this linear recurrence relation is also the sum of two parts called as homogeneous solution and particular solution. The solution of this linear recurrence relation is the sum of two parts. One is called as the homogeneous solution, another is called as the particular solution. Homogeneous solution is obtained from the homogeneous part of the equation. Now, what I mean by homogeneous part? Homogeneous part means the free from Fn term. The free from Fn term means this term of this recurrence relation we called as the homogeneous part. So when I'm finding the homogeneous solution, we are supposed to use this homogeneous part, and when we find the particular solution, we'll use this function of Fn. That means what? If Fn for a linear recurrence relation is 0, its particular solution will also be 0. Now moving on, how to find the homogeneous solution. How the homogeneous solution of a recurrence relation is obtained. Now as we know, the solution of a differential equation is in terms of exponential. Its solution is exponential, like e to the power ax kind of solution. This solution is also exponential, but over here base is not e. Over here base can be changed in terms of any real number. So over here, how to get homogeneous solution? For that, we are supposed to make a equation called as auxiliary equation. And for this, we are supposed to put an equals to r to the power n in homogeneous part of first. That means, what exactly it means? It means that we are assuming that the given equation is having the solution of the form r to the power n. What is r over here? It may be any real number. Now, when I substitute this in the homogeneous part of the equation, what I get, Cn into r to the power n, Cn minus 1, r to the power n minus 1, C0, r to the power 0 equal to 0. It's important to take equal to 0 because we are paying attention only on homogeneous part. Now, if you see, this is not a power r, r power n, sorry. This should be r power n. Now this is a polynomial equation of degree n. Now we will find its roots, and it will have n roots. Suppose that the roots of this equation comes out as, let the roots of the equation comes out as r1, r2 up to rn. Now the roots of the equation comes out as r1, r2, rn. Now depending on the nature of the roots, the homogeneous solution will be written. As in differential equation solution, we do have three cases: real equal, real unequal, and complex. Over here, we are only considering two cases for writing the particular homogeneous solution. Case number one, if roots of the equation are unequal. Unequal means does not matter real or imaginary. We are only considering roots are unequal. That means R1 is not equal to R2, R1 is not equals to R2, not equals to R3, means every roots is different. So in this case, the homogeneous solution, which is denoted as ANH, homogeneous solution for the recurrence relation, equals to the constant b1 into first root to the power n plus constant b2 second root to the power n, and so on, bn into rn to the power n. If the equation is having n roots, then this is how the homogeneous solution of that recurrence relation will be written. Where what is these b? These bi's are some of the constants, same as c1 e to the power ax plus c2 e to the power bx plus c3 and so on kind of thing, relating with the differential equation. Now suppose that if equation is having only two roots, write it up to b2 only. So b1 r1 to the power n plus b2 r to the power n. If only one root, up to first. If three roots are there, do write up to r3. Okay, this is the general formula. As per the number of roots the equation is having, we are supposed to write it. Now moving on for case number 2. This case says that if roots are equal, if roots of the equation are equal in nature. So suppose I am taking case of two roots. Suppose the equation is having two roots and both of them are equal. Suppose their common value is r. So in this case, the homogeneous solution of the equation is written as b1 into r1, b1 into r1 power n plus n times b2 into r2 power n. Now, why this n comes out, I will explain this too, which can all r1, r2 is same. So that means b1 plus n times b2 into that r power n. So this is how we write the solution when the roots of the equations are equal. A1 plus A2n, or not A1, B1 plus B2n r power n. It does not matter whether I am taking B1, C1, D1, all of them represent the constant. So this is how we are getting. So now when the roots are equal, the thing is what we are supposed to make both the solution as linearly independent. To make that thing true, the one of the coefficient need to be multiplied by n, need to be multiplied by n. If I extend this case, if three roots are equal, R1 equal to R2 equal to R3, let the value is R for them. So in that case, what will be the homogeneous solution? It will be B1 plus B2 into n plus B3 into n square into R power n. That means the number of root, the number of arbitrary constant arbitrary, these vi are called as arbitrary constant. Now try to explore the difference between constant and arbitrary constant. Okay, so this is how we write it in terms of three roots. So three roots means three coefficient. Till b3 we are supposed to write. If four roots are equal, write it till b4, and in b4 it will comes out as n to the power 3. It will comes out as n to the power 3. So these are the two cases. On that basis we can write the homogeneous solution of the recurrence relation. Now, it's not always that an equation is having roots in a specific case. The roots can be the combination of the two. For example, suppose I solve the equation and its roots comes out as 4, 5. Its roots comes out as 4, comma 5. So what will be the homogeneous solution for this? The homogeneous solution will be b1 into first root to the power n plus b2 into second root to the power n. On the same side, if roots are equal, suppose I get the roots of the equation as 4, comma 4, comma 4. Repeated root, case number 2. So in this case, the homogeneous solution will be written as, apply the repetition for three roots. So b1 plus b2 into n plus b3 into n square to the into r. What is r? The common value to the power n. This is the second case when roots are equal. Now let us take a combination of the two. Quite interesting one. So now this time roots are comes out as 4, 5, comma 6, comma 6. Now what did you say for this? Can I say all the roots are distinct? All the roots are unequal? The answer is no, because 6 and 6 are same. Can I say all the roots are equal? The answer is no, because 4 and 5 are different. So in this scenario, we'll apply the combination of the two. Let us see how. So homogeneous solution will be, first to different root, apply the case number 1. So b1 plus b1 into r1 power n means b1 into first root power n plus b2 into second root power n. This is done for the unequal case. Now plus the equal case for two roots now. Since b1, b2 already used, we'll use b3 and b4. Do remember, the arbitrary constant should not be repeated, into 6 power n. So this is the final solution. Final means the final homogeneous solution for this recurrence relation. Even though if conditions are given, we can find the values of these arbitrary constant too. I hope you understand the concept. Let me take an example, direct a problem that how we'll find the solution. So suppose that the question is asking find all the solution. All the solution means homogeneous plus particular of, let me write a equation, an plus 2 minus 6 times an plus 1 plus 5 times an equal to 0. Or in place of 0, I can take some function of n. Some function of n. Okay, so let us try to find the homogeneous solution. We'll put as an equals to r to the power n in homogeneous part of first equation. So this is the homogeneous part of this equation. So what I will get, an is r power n. So an plus 2 will be r power n plus 2. So in place of n, put n plus 2. An plus 1 will be r power n plus 1 because an is r power n plus 5 times rn equals to 0. I can take r power n common from here. What left? R square minus 6r plus 5 equal to 0. Now the product of these two terms 0. That means either both or one of them must be 0. But r power n can't be 0. Why? Because we are assuming this is the solution. Okay, and we are finding the non-zero solution, non-trivial solution. Okay. So what left? R square minus 6r plus 5 equal to 0. Now find the roots of the equation. The factors of 5 whose sum comes out as 6. So it will be what? 2 plus 3. So r minus 2, r minus 3. R minus 2, r minus 3 equals to 0. So r square correct. Let us check it they are correct or not. So r square minus 3r minus 2r 5r. The factor of 5 whose sum is 6. So not minus 2 minus 3. 5 plus 1 should be there. So r minus 5 and r minus 1 equal to 0. Let us check it again. R square minus r minus 5. Yes, this is fine. So r equals to 1 comma 5. The roots of the equation that we obtained is 1 comma 5. So what will be the homogeneous solution for this equation? It will be b1 into first root to the power n plus b2 into second root to the power n. So this is how we get the homogeneous solution of this equation, and I hope you understand this. So overall, if I summarize this session, what we discussed that if a recurrence relation is there, how to find its homogeneous solution. For finding homogeneous solution, we are supposed to put an equals to r to the power n, find the roots of the equation. As per the roots of the equation, we are supposed to write it. Now, is this the final solution? No, because the solution also consists of particular solution. That how to find A and P, particular solution, which is based on Fn. So in the next session, we'll try to learn that how to find Fn for a recurrence relation. I hope you understand it. If there is still any concern, you can take a look once again on the video. Leave your comment if there is any concern related to these concepts. Now let us close this session.